Okay, welcome everybody to my talk today. Well, my name is Christian and I will present you work done by the University of Copenhagen, the Max Planck Institute for Informatics and the German Research Center for Artificial Intelligence, namely the system GazeProjector. So the talk is structured as follows. First I will give you a motivation about the topic, then I will talk about some related work, and in the main part I will present the developed system and the evaluation we did with it. And finally, I will conclude with the limitations and an overall conclusion. So let's start with the motivation. Well, there are many settings around us where we are confronted with large displays. For example, large display walls can be used in control rooms, or in museums we can find displays of arbitrary size that are showing information about the exhibitions to people. Also in showrooms or art galleries, displays of different sizes and types like TV-sized screens, tablets, or even projections are used to present several kinds of content to people. On the other side, Gaze is a powerful input modality to interact with all these displays. The advances made with head-mounted eye trackers, making them cheaper, increasing accuracy, decreasing weight, make them ready for such pervasive display scenarios. But usually these eye trackers have to be calibrated to the specific display someone intends to interact with. And as people usually might walk around in such pervasive display settings, we always might end up in the same problem. That every time a user changes orientation and or position in front of such a display, the head-mounted eye tracker has to be calibrated to keep a high accurate gaze estimation accuracy, which is the basis for smooth interaction. So with GazeProjector, we aim to resolve this issue. And therefore, our goal is made up by the following three contributions. So first, we want to realize location and orientation independent gaze estimation on a display of varying size and resolution without requiring any instrumentation in the environment. Second, we want to achieve an accurate gaze estimation on arbitrary displays in the environment without requiring to recalibrate the system for each display independently. And third, we want to maintain a high gaze estimation accuracy without requiring to recalibrate the system when the user changes position and or orientation to the displays. So how does GazeProjector work basically? Well, in total we have 3 steps to achieve the mentioned goal. So initially we have to calibrate the pupil positions to the scene camera's coordinate system, which is the usual way when you're using head-mounted eye trackers. Note that we calibrate on an arbitrary screen in the environment. Second, we will track the spatial relationship between the eye tracker and the specific display from the eye tracker's perspective. That means that we won't use any external tracking system to do this. And using this, we will map the 2D gaze positions from the scene camera's coordinate space onto the display's coordinate space in the last step. Well, knowing the basic principle of GazeProjector, it's time now to talk about some related work. Well, our work builds on methods for gaze approximation and estimation on displays, on gaze interaction using head-mounted eye trackers, and as well as tracking the spatial relationship between users and displays. For reasons of brevity, I will just concentrate on gaze-based interaction. More details to the other 2 topics can be found in the paper. Well, gaze-based interaction using head-mounted eye trackers usually allow people to freely move around. And I would like to point to 2 works done in this area that make use of the advances made in computer vision. So often AR markers are attached to screens or surfaces in the environment to track them and identify them and map gaze accordingly. Madenbegi and Hansen substituted these commonly used AR markers by detecting the screen directly in the scene camera's video stream. And they do this by looking for quadrilaterals, which are polygons containing 4 edges, describing the standard form of the display. Turner et al. Extended this approach to a multi-display scenario where they attached a second camera to the eye tracker to extend the visual field in the vertical axis, so they were able to cover devices held in hand. And the system has to be calibrated to both screens a priori, and then it automatically switches calibration according to the display visible in the camera stream. Well, both approaches differ from GazeProjector as they require the display to be fully visible in the scene camera's view. And as the approaches rely on the screen borders for screen detection, they are not that robust against changing lighting positions, and even more, they are restricted to this special kind or type of display to be kind of rectangular. So let's come back to GazeProjector and see how it works in more detail. Well, in our implementation, we are using a head-mounted eye tracker from Pupil Labs. Since it's open source for development, it's relatively cheap, and it comes with a high accurate gaze estimation out of the box. And as already mentioned, the first step is to calibrate the pupil positions to the scene camera's coordinate system. And this is done by using a 9-point calibration procedure while gazing at an RR marker that is shown at 9 different points around the screen. So after the calibration, the interesting part of the system starts. Let's have a look at a multi-display scenario. So here, user is standing right in front of a large projection wall. And the scene camera of the head-mounted eye tracker captures the environment right in front of the user. And according to the distance to the display, these images contain parts of the screen's content someone is currently facing. And in addition, the eye camera is tracking the pupil. All this information is sent to a central server. And this central server is also aware of all screens in the environment, as well as their current content and their physical size. But note that the server does not have any information about the location in space of these displays. The main idea now is to use the screenshots, the current screenshots, as templates which tries the server to find in the observed images of the scene camera. Therefore, we make use of natural feature tracking algorithm to extract features out of the images. And if we found a match between the feature points, the system calculates a transformation matrix, namely a homography, describing the transformation of points from one image plane, namely the scene camera's frames, to another image plane, namely the display screenshot. We are then using the initial calibration and multiply the 2D gaze point of the scene camera's coordinate system with that homography matrix, and as a result, we obtain the projected 2D gaze point on the display. Well, to investigate the performance of our system, we also did an evaluation which consists of 2 experiments. In the first experiment, we were using a single display scenario with a large projection wall. We've chosen 6 different locations in front of the screen, 3 near and 3 far, to simulate a more realistic setting in which people are frequently changing positions, distance, and orientation to the display. To compare our approach to existing solutions, we implemented 3 modes in the first experiment. First one is a marker tracking mode, in which we attached visual on-screen markers to the display wall to track it and map gaze accordingly. The second mode, the head orientation mode, we used an OptiTrack system to track participants' head and then map gaze accordingly. And in the third mode, we used GazeProjector as described before. The task now was that people had to gaze on 9 different targets shown in random sequential order on this large projection wall from all 6 locations. And for each mode, participants were calibrated from 2 positions, namely L2 and L5, placed centrally in front of the display to investigate the effect of changing the distance between calibrations. And here you can also see the background that we used for feature tracking and the markers we used for marker tracking. So the results of the first experiments we got were the following. First, we found that GazeProjector performed a lot better than the other modes and achieved a significant lower gaze estimation error. We also found a main effect for mode. That means that we found significant differences within marker tracking and head orientation between both calibrations. We did not find such an effect for GazeProjector. Even more important, we found that GazeProjector using near calibration showed the lowest error and differed significantly from the other modes. And GazeProjector using the far calibration showed the second lowest error, as you can see with the both green bars in the box plot. We also found a main effect for location. That means that back positions performed better than front positions, and people tend to move their head quite more often than moving the eyes. Possible explanation for these effects are first, that when calibrating at far positions, you obtain a much smaller calibration plane in the scene camera's view than for near positions. And then it could be the case that if pupil positions lying outside this calibration plane, the eye tracker has to extrapolate, which leads to more inaccurate results. And even more for back positions, it was often the case that people did not have to move their head that much than for near positions to look at all the shown targets. In the second experiment, we used the multi-display scenario. That means that we used the same large projection wall, but in addition added a Microsoft Surface tabletop and an iPad Air screen. Here, people were free to move around in front of the screen and to simulate a more realistic scenario in which people are really moving around during gaze estimation on several screens. We had only 2 modes in this experiment, therefore we chose marker tracking, where we placed the on-screen markers on all screens, and GazeProjector, as described before. We did not use head orientation, as we believe it would deliver similar results across multiple screens. Here we calibrated again from L2 and L5 as in the first experiment, and in addition recorded calibrations for the Surface and the iPad to investigate the effect of calibrating on a screen not orthogonal to the user and on a screen with a considerably smaller size. And the task was the same as in the first one. People had to gaze on 9 different targets on each screen, shown in random sequential order. Here you can also see the backgrounds used for feature tracking. The results we got from these experiments were the following. So first, GazeProjector performed better than marker tracking, significantly better. We found a main effect for mode, meaning that GazeProjector using near and far calibration showed a significant lower error than marker tracking, calibrated at far on the display and on the other 2 screens. And we also found that GazeProjector calibrated and or used at Surface and iPad showed a significant lower error than marker tracking calibrated or used on these screens. And again, GazeProjector with near calibration showed the lowest error, followed by the far calibration. Even more interesting, we found the main effect for screen. That means that the wall performed a lot better than the other screens. And as you can see in the box plot, GazeProjector often outperformed marker tracking. So possible explanation for the bad results of the marker tracking for the two displays here is that it was often the case that displays overlapped in the scene camera's view, and therefore also the markers for the marker tracking overlapped. And in these cases, the system then couldn't decide which screen is really lying in the direct focus of the user. So despite these good results, we also have to deal with some limitations. So first, our current implementation relies on the streaming the screenshots from the displays and streaming all eye tracking data from the eye trackers. And if we then increase the number of displays or the number of eye trackers, we also increase the network load. Second, the system relies on the quality of image data, so it could be the case that if the representation of the screen in the scene camera images is too small, we can't find enough features for an accurate tracking. And as with all optical systems, environmental factors such as changing lighting positions can affect the video quality. And as said, the accuracy is dependent on the number of features, so we have to use feature-rich content on all screens. Well, let me summarize what we did with GazeProjector. So first, GazeProjector is suitable for pervasive display settings, as our results showed that we could achieve better results according gaze estimation accuracy than using an external tracking system, which would also be expensive to set up. And we also achieve better results than using a marker tracking approach, which would reduce the screen space available for content. Secondly, with GazeProjector, we enabled interaction from arbitrary locations and orientations without the need of using any external tracking system and without the need of recalibrating every time someone changes position and orientation. And we could also maintain a constant gaze estimation across multiple displays, even if we calibrate it on an iPad screen or on another smaller screen. And as GazeProjector relies on natural feature tracking approach, it only requires displays to be partially visible in the scene camera video frame, and we found that usually a quarter is enough. And last but not least, we plan to release the code soon as open source, so that every one of you can enjoy it and make cool things out of it. So, thanks for your attention, and I'm open for questions.
Thank Christian, and if you guys have any questions, please raise your hand or come up to the mic. All right, while we're waiting for some inspiration for questions, I'll ask some. It seems that the differences that you're observing in your experiments stem primarily from the mode, but also from the calibration that you use. In essence, you're treating this is a 3D calibration problem, but you're actually having a 2D target. So there's, as expected, there should be a very large effect of what distance do you actually calibrate the system at. Can you tell us the reasons why and how, what kind of improvements would you see if you actually really did a complete 3D calibration? Because you really then wouldn't have a problem between near, far, surface, iPad, wall, and whatever.
So you mean when we are tracking the 3D position during calibration? Yeah.
Right.
Yeah, it could help to overcome this issue to calibrate on different planes. So, yeah, the problem is that you calibrate at different distances in the Z direction. So, and we thought that in a real application case, someone is calibrating on a private own device, which hold in hand directly in front of the face, and then also this effect wouldn't occur since the calibration plane would be big enough. So, yeah, we think that this is one application scenario where we can resolve this issue. But you are right. Tracking the 3D position during calibration can also be used to overcome this limitation.
It's not just the 3D position where you are during calibration, but it actually, what you're really calibrating against is, you're doing this in plane, in an image, but really what you should be calibrating is rays, and once you do that, you can adjust it to any different particular plane or aspect or anything like that. But you're observing in your second experiment, if I'm correct, for when you calibrate for the very near distances like the surface or the iPad, you actually have a worse performance than the marker tracking in that case, and when you calibrate for the far ones, you have better. So you're clearly kind of in this space, and your calibration have a lot of impact onto the overall results that you're observing.
Yeah. Also, it was the case that when calibrating on surface, it was not orthogonal to your face, so this created more distortion in the calibration plane, and then it was much more difficult for the eye tracker to resolve this internally.